Welcome to this tutorial on industrial instrumentation. Today we will talk about temperature measurement part 4 and the topic of discussion will be resistance temperature detector, also known as RTD. The topics that we'll cover in this discourse are the general principle of resistance temperature detector, then we'll have a look at the numerical equations, then we'll see the construction and the calibration of RTDs. Finally, we'll end up with concern areas of RTDs and its limitation and advantages. The resistance dependent thermometer or resistance temperature detector is also called the resistance thermometer. It is the first of the three main types of electrical temperature sensor, the other two being thermocouple and thermistor. In this type of sensors, some electrical parameter changes with the change in temperature. In RTDs, there is a predictable change in the resistance value with changes in the temperature. The materials used to construct the RTDs are generally pure metals like platinum, nickel, or copper. Few other metals like tungsten, silver, and gold are also used as RTD elements. The RTD elements are fragile and therefore are placed in sheeted probes to give them mechanical stability. The resistance versus temperature relationship tells us about the value of resistance change in the sensor per degree change of temperature. The sensor elements like the platinum, nickel and copper have repeatable R versus T curve. Platinum is the noble metal which is chemically inert and has the most stable R versus T relationship over the largest temperature range from -272.5 degrees Celsius to 961.78 degrees Celsius, making it the best RTD candidate. Nickel R versus T tends to become nonlinear beyond 300 degrees Celsius, and although copper has a linear reading over a significant temperature range, but it gets oxidized at moderate temperature and therefore cannot be used beyond 150 degrees Celsius. The PT100, PT500 and PT1000 are standard calibrated RTD circuits with 100 ohm, 500 ohm and 1000 ohm of platinum resistance wire at 0 degrees Celsius respectively. Other RTD elements are calibrated against the PT100. The RTD elements generally have PTC, that is positive temperature coefficient, which means resistance increases with increase in temperature value. The RTD normally has a linear output scale for a significant temperature range, but beyond that range it loses its linearity. The calendar Van Dusen equation is used to determine the resistance value for the RTD temperature sensors and is given as in equation 1 below, having three constant values in this expression A, B and C. We see that the temperature scale is more nonlinear in the range of -200 degrees Celsius to about 0 degrees Celsius, and the nonlinearity is reduced between the range of 0 degrees Celsius and 850 degrees Celsius. However, there is a simpler and linear resistance to temperature relationship that acts as the working formula in RTD operation as shown below. Here, alpha is a function of the sensor element's resistance value at both 0 degrees Celsius and 100 degrees Celsius. We have the equation RT equal to R0 into 1 plus alpha del T. The device sensitivity is calculated as sensitivity is equal to dr by d del T, and alpha is given as R100 minus R0 by 100 into R0. Pure platinum has alpha of value 0.003925 per degree Celsius. Copper has alpha of 0.004 per degree Celsius and nickel has alpha value of 0.0068 per degree Celsius. The alpha value changes based on the doping. The RTD elements act like electrical transducers when temperature changes cause resistance changes. The metals that are used in RTD sensors are pure, uniform, stable, reproducible elements with good coefficient of resistance and capacity to withstand repeated temperature change cycles. The RTD element is in a spring-like wire shape surrounded by porcelain insulator and finally enclosed in a metal or alloy sheet. The insulator is made up of PVC or silicon rubber or polytetrafluoroethylene known as PTFE. The insulator prevents short circuit between the metal sheet and the RTD wire. The RTD sheet is made up of Inconel, which is an alloy of nickel chromium, and this is used as it is corrosion resistive. Sometimes stainless steel is also used as the external metal sheet. The RTD circuit comes in three configurations: 2-wire, 3-wire, and 4-wire. The 3-wire configuration is the most commonly used configuration. We'll have a deeper look at the 2, 3, and 4-wire configuration in our next discussion. There are three main categories of RTD sensors, that is thin film, wire wound, and coiled element. The thin film elements are formed by depositing thin layers of resistive material, usually platinum, on a ceramic substrate coated with epoxy or glass, acting as a strain relief. The film thickness is 10 to 100 Armstrong units. The thin film elements perform best between 300 degrees Celsius and 500 degrees Celsius. The platinum wire wound coil is used for very high temperature measurement, that is above 950 degrees Celsius. Their structure provides free expansion and contraction, but they are sensitive to vibration and shock. The coiled element has largely replaced the wire wound elements as they expand more freely than the previous type, and also they are free from strain effects. The base metal here is also platinum that is placed inside bore of mandrel and then packed with very fine ceramic powder. The coiled element RTD can measure up to 850 degrees Celsius. The standard platinum resistance thermometer, known as SPRT, is also a coil element RTD that can measure from minus 200 degrees Celsius to about 1000 degrees Celsius. Carbon resistance is used for ultra-low temperature, that is in the range of minus 173 degrees Celsius to minus 273 degrees Celsius. Carbon resistors are inexpensive and reliable at extreme low temperatures as they do not suffer from hysteresis effect. The RTD is an electrical temperature sensing device that requires proper calibration before usage. There are two calibration methods for RTD, and those are fixed point method and compression method, which is performed at temperature other than 0 degrees Celsius and 100 degrees Celsius. In the fixed point calibration method, the device is calibrated for very high accuracy, and the method uses triple point, freezing point, and melting point values of pure substances like the water, zinc, tin, and argon to measure the known temperature repeatedly. This method calibrates the RTD, providing the RTD an accuracy of plus minus 0.01% and resolution of plus minus 0.001 degrees Celsius. The calibration method involves ice bath for industrial grade probes, and this method can be carried out simultaneously for multiple RTD sensors. In the second method, that is compression calibration method, a secondary device is used which is generally standard platinum resistance thermometer SPRT. The industry grade RTDs are submerged along with the SPRT and the process is repeated several times. Unlike the fixed point method, the calibration can be conducted over a wide temperature range between minus 100 degrees Celsius and 500 degrees Celsius, excluding the 0 degrees Celsius and 100 degrees Celsius points. In this method also, several devices can be simultaneously calibrated. The that are used are silicon oils and molten salts for the calibration purpose. There are few areas of concern associated with the RTD which require close and timely monitoring, and these areas are lead wear and self-heating induced in it. development of thermal EMF, the sensor's stability, repeatability, hysteresis, and stem conduction should be checked at a timely interval. The calibration and the interpolation are also changed and therefore they should be recalibrated. The insulation resistance is prone to wear and tear and therefore call for proper and timely maintenance. The advantages of the RTD are that it is significantly accurate, it has very small size, the sensor provides wide operational range from minus 200 degrees Celsius to about 650 degrees Celsius for the average purposes. They have fast response speed, good longevity and high stability. They also offer good sensitivity. There is no need for any temperature compensation in this type of RTDs, fairly linear scale of operation within a significant temperature range. The radioactive radiation has little effects on the RTD elements. However, there are few limitations which are it is significantly costly. The sensor requires both external power supply and a bridge circuit for operation. The resistance heating effect and the bridge current are potential error causing areas. The vibration in the measuring area abuses the sensor mechanically affecting its result. The size is bigger than the thermocouple and the response is slower than the thermistor. The readers can refer to the following links and references for more detailed and elaborate study. Thank you.